Hey gang, welcome to Computer Graphics on a bright and happy Monday morning. Today we're going to be talking about illumination. We'll begin talking about illumination. We're going to start off talking about lighting and color. We're going to spend a little time trying to understand what is light, what is color, and how do humans perceive these things? So that's what we're going to talk about today. And you might think, as I get started, well, what does this have to do with computer science? It actually has everything to do with computer science, because the way we visualize things in computing is we have displays, and those displays are based on RGB technology. You might have heard RGB. What is RGB? Well, it's red, green, and blue. Those are the primary colors. And you may have heard that. You may have wondered, well, but what does that really mean? And why did they choose red, green, blue? And you know, I don't see just red, green, blue. You know, I see lots and lots of colors on my display. So how does that all work? To understand it at all, or in any depth, you really kind of need to understand what is light, what is color, and how do humans detect these things, what sort of sensations it causes. So let's get started by sharing the notes here. So, and again, it's we're starting in chapter 15, which is called Light and Color. What is light? Well, light is really just a tiny part of the electromagnetic spectrum. That's all it is. And in this diagram, it kind of breaks out visible light and puts it in the context of the broader EM spectrum. So it's all the same thing. It's just the wavelengths that we're talking about here. So if you get to really, really short wavelengths, you have like gamma rays that come from stars and colliding black holes. And then you have X-rays, right? And these are what, you know, doctors use to see inside you, right? And then you have the ultraviolet, which was a movie, I think, at one point in time. But it is, you can think of it, now you can start, because it's getting close to the EM spectrum, you can think of it as a violet that's darker than violet, okay? It's ultraviolet. You can't see these colors, you can't sense them. But again, they're just like colors. They're just outside our range. And then you get into the visible spectrum that goes from, you know, the violet, indigo, blue, green, yellow, orange, red, and then that takes you into the infrared, right? Infrared. Humans can actually sense infrared, not at the resolution that we can sense light. How do we sense the infrared? Anybody know in chat? How do humans sense infrared? It's warm. Exactly. You detect infrared as heat. So, you know, we have skin, and we have these little pain sensors. You know, well, they go to pain if the infrared gets too far, right? It can harm you physically, right? It can burn you. And so we have sensors, the pain sensors kick in. But before we get to pain, you know, we can feel warmth. You just don't have any kind of focusing mechanism or anything like that. So you can't see infrared, but you can sense it. You sense it through heat, right? And then it moves towards pain, and it moves towards pain because infrared, you know, is heat, and too much of it, you know, will burn you and destroy you. So it's very important to have sensors for that. And then beyond that, we have our microwaves. We use those to cook food, right? Jiggles those water molecules really fast. That causes things to heat up, because really all heat is the movement of molecules, right? And then beyond that, we have radio waves, and we're bathed in radio. We're bathed in all of these things, right? But radio waves, right? That's how our cell phones communicate with one another. So anyway, the point is there's nothing different between a microwave or the color green or an X-ray except for the wavelength and the frequency of the EM energy. So light is often characterized by its wavelength expressed in nanometers, sometimes by its frequency measured in terahertz. So if you look here, this scale down here, this came from Britannica Online, and they take the spectrum and they use 3 different scales, 3 different ways of describing it. The vast majority of references will talk about, green light being, near 550 nanometers. So with wavelengths of near 550 nanometers, they have it shown at 510 here. It varies a little bit from source to source, because what is green? Well, there's a spectrum of green. So is green here or is green here? Different people put it different places. So that's why there is no actual wavelength number that everybody agrees on is the perfect wavelength number for green light. But anyway, we can talk about wavelengths. Yellow being around 570 nanometers, the wavelength. And when I say wavelength, right, I'm talking about the length of a wave is, for yellow, 580 nanometers. That's the length of that wave. You can also talk about frequency, which is, how many up-downs did it go through per unit time. And again, these things are in the trillions of cycles per second. They're in the terahertz range. So anyway, that's the visible spectrum here. And it's important to start off by saying that humans have attached names to many of the wavelengths of light. Humans have attached names to these wavelengths. So a lot of times I'll say red when instead of saying 650 electromagnetic energy at 650 nanometer wavelength. It's just easier to say, oh, that's red, right? Rather than saying it's electromagnetic energy with a wavelength of 650. Or I might say green instead of saying, oh, well, it's light at, it's light electromagnetic energy with a wavelength of 550 nanometers. Or I might say yellow instead of saying, oh, light that's about, with a wavelength of about 580 nanometers. Okay, so that all makes sense. Okay. Now, in addition to color, and Andrew, I'll grab your question later when we get into color in more depth. In addition to color, there are other qualities of light. We try to capture the, I guess you might say, intensity of the light. And we've got different words for that. We've got radiance, we've got luminance, we've got brightness, we've got luminescence flux. So what is radiance? Radiance is just the total amount of energy that flows from an electromagnetic source. And that is electromagnetic energy of all forms. So light and heat and X-rays, etc. So if you think about an old-fashioned incandescent bulb and you go to the supermarket, you might say, oh, here are the 60-watt light bulbs. Here's the 100-watt light bulbs. Here's the 30-watt light bulb. And we basically know the higher the number, the brighter the light, right? So a 100-watt light bulb is brighter than a 30-watt light bulb. And that's the way old-fashioned incandescent light bulbs are sold. But really, that 60 doesn't mean 60 units of light in some unit for light. What that 60 means, it's measured in watts. So it's the amount of total energy. And if you've ever touched an incandescent light bulb while it was lit, and you probably did as a child because children are curious and they want to touch and eat everything. When you do that, you burned your little fingers, right? And you learned an important lesson that incandescent light bulbs get very, very, very hot. And if you think about it, that means that incandescent light bulb, right, while it might be producing light, right, and that's the reason why we call it a light bulb and we have it, it's also producing a lot of energy up here, right? So an incandescent light bulb is generating a lot of heat, and only part of that energy generates light. If you think about human history, really, as technology progressed, we've tried to find better and better light sources that produce more light more cheaply and less things we don't want, like heat. So if you think about, like the first thing, a fire. Well, fire mainly produces heat, right? It produces some light, right? And so, we've all sat around a campfire and both felt its warmth and its and enjoyed its light. But it tends to be a reddish kind of light, a yellowish reddish light. And that makes sense because it's mainly centered over here in the infrared. You're burning stuff. And then if you think about, a torch, not in the British term, but in the American term, having a torch, that's just fire. If you think about a gas lamp, we don't have those anymore, but in the 1800s, that was the standard way of lighting. That was just a little gas flame. But gas flames tended to burn bluer, and so they didn't generate more light. But still, obviously, it's a flame, so it's generating a lot of heat, but at least it generated more light, right? Though you were burning stuff. Candles are just like, they tend to, of course, be reddish yellow because, again, you're just burning something. So the incandescent light bulb was a huge advance, at the early part of the 20th century, the last part of the 1800s. So you were running electricity through a filament, and that's how you were getting your light. So you were getting a lot more light. So basically, the whole deal is we've wanted things that are brighter and brighter, that give you more and more light for less and less overall energy. So, convert more of that energy to light. So light sources were used to be, light bulbs were measured in watts, which is a measure of radiance. And we've talked about the downside. Now, I keep saying brighter. What is brightness? Well, I'm gonna jump ahead because the way I presented this, I actually don't define brightness until the end. But here's what brightness is. Brightness is a subjective measure of the perceived intensity of light. It's subjective. You can't measure brightness. There's no, you can measure it in the sense of saying, oh, A is brighter than B, right? But there's no unit of brightness. And that makes sense because how bright is a candle? Well, if there's been a power failure and I'm sitting at home alone in the dark and I light a candle, it lights up the room. It's a flickering yellowish orange light, but I can see. And so the candle is quite bright. In fact, if I stare directly at the candle for a little while and then look away, well, it's hard to see because there'll be an after image of a candle in my retina, right? So a candle in a very dark room can appear very, very bright. But take that candle and light it, the exact same candle, and light it out of doors at noon. Well, you can see the flame, but it barely produces any light. It's not bright at all, right? So brightness is completely subjective. It depends on the environment and tons of other factors. So we say brightness, something is bright or dim all the time, but you can't really, there's no unit of brightness. There's no measurement of brightness like there's a watt. So another thing is that your sensitivity to light varies based on the wavelength of that light. What am I trying to say here? It takes more red energy. It takes more electromagnetic energy at the frequency of red, the wavelength of red, than it does to generate a level of perceived brightness than it does under exactly the same conditions for green. In other words, you're more sensitive to green than you are to red. So let's say to reach a particular level, of brightness in fixed conditions, so the level of the lighting in the room, whatever, all that's the same. But to get a particular level of brightness of red light is going to require more energy than to get that same level of brightness from green light. Now, why is that the case? Well, because your sensitivity to light varies based on wavelength. And you might say, well, that seems weird, Mike, but it shouldn't seem weird at all. It should actually seem like it has to obviously be that way. Why do I say that? Well, let's go back to the very first diagram that I showed, right? Here's the visible light, right? And it sits between things you can't see and other things you can't see. So it would be weird if suddenly there was like some switch that went ping, and so now I can sense all of these wavelengths with equal sensitivity up to here, and it goes ping, and so and suddenly I'm blind again to it. What wavelengths are in the middle? That's what we call greenish, right? So we would expect that we would be most sensitive to energy in the center portion of the range that we can detect, right? Another way of saying that is you're less sensitive to red and you're less sensitive to blue than you are to green. So if you want a certain intensity of green to be the same as the perceived intensity of red, you're going to need more red energy than you're going to need green energy, because you're less sensitive, your eye's less sensitive, so you got to jack up the volume, right? Jack up the power to bring it up to the same level that you would have of green. And same thing for blue. And in fact, that's what this little diagram here is showing you. There's this little curve here, and it's showing you how your sensitivity is peaking right around green, yellow, right? And then it drops off in the red. And so this curve is your sensitivity to light, and it peaks, like I said, somewhere in the middle of the spectrum that we can detect, which makes sense. You might say, but there are two curves here. Why, Mike? Well, this red curve is the standard. It's the daylight curve. It's the photopic, if I'm saying that right, curve. This is the curve in which both your rods and your cones are active. The color cells, you've got two types of cells in your little eyeball. You got rods and cones. rods detect light, but they don't tell you what color that light is. The little cones, you've got three types of cones. We'll talk about those in a minute, but those cones are how you detect color. Cones are actually less sensitive than rods. Rods are more sensitive. And so here is when you're just viewing in dim lighting, and that's I have the word for it here. That's the scotopic conditions, and basically that's when it's near dark, and it shifts towards the back, a little towards the left in the spectrum that we can see. So basically, in daylight hours, our little cones are actually sensitive to frequencies that are a little bit shifted than our rods are. It makes sense. They're two different systems, so it'd be weird if they were identically aligned. Okay, so that's that. So we've talked about watts, we've talked about radiance, and we've talked about brightness. And I said there's no unit of measurement for brightness. Well, we do have something called luminance and something called luminous flux. Luminance is measured in candela per square meter, and it is the total light emitted or reflected from a surface in a given direction. Luminous flux is almost exactly the same thing, but it is that total light emitted in all directions by a light source. So when you buy a modern bulb, when you buy an LED bulb, it won't say how many watts it has. Well, you might be able to search and find that. It'll say how many lumens the bulb produces. And that's basically telling you, okay, how much light does it produce? So the total amount of light, regardless of what direction it is, the total amount of red, green, all across the spectrum, but just within the visible spectrum, that is the number of lumens that's generated by the source. If you're interested in that falls in a particular direction, you're now talking about luminance rather than luminescent flux. And so if you're talking about light going in a particular direction, well, then you have to talk about where it lands, and that's why that's measured in candela per square meter. But usually when we're talking about, it's really luminous flux, but a lot of times when you're talking about luminance just in general, people go, oh, lumens measure luminance. Well, technically it measures luminance flux because you're not concerned about the direction. You want to know the total amount of light generated in all directions. So if you look, I was talking earlier about our whole direction has been towards more light and less waste heat in our technology. And now modern bulbs are LED bulbs. If you've touched an LED bulb, it gets hot. You can burn yourself on an LED bulb, but it is tons cooler than you can touch your finger to an LED bulb, a bright LED bulb, and you're not going to burn yourself. Now, of course, it depends on the size of that. It depends on the energy that thing is generating, because if I can make my phone pop up for a sec by moving it, squiggling it, our phones have a little LED on the back of them for our cameras, and of course you can touch your finger to that and it's not warm at all, and yet it's generating a lot of light. So there is efficiencies, but an LED bulb that you screw into a normal light socket, that still gets rather warm. It gets hot, but it's not as hot as what you get if you from an incandescent bulb. And all that means is basically that LED bulbs are more efficient. Incandescent bulbs generate about 15 lumens per watt, where LED bulbs generate about 60 lumens per watt. And so they're about 4 times more efficient at generating light. Now, if you're interested in heat, if you're cold, right? if it's wintertime and it's cold in your house, the waste heat from your 120 watt light bulb isn't waste heat. It's useful heat. But most of the time we want our lights to generate light, and we want our central heating to generate, warmth. And so in that case, it is waste heat generated by light bulbs. Now I say that, but like when I was a kid, and I don't know, maybe they still existed when you guys were kids. I don't think so. They probably died out long before. But there was something called easy bake ovens, which were little ovens for kids back when we were obsessed with giving gender specific toys to girls and boys. Little girls were given easy bake ovens, and basically it was a little oven that had a light bulb in it, but like a 120 watt light bulb, and they had special little recipes that basically, you mix up a little teeny tiny cake, and you put it in the easy bake oven, and the heat from the 120 watt light bulb would cause it to bake its little cake. I used to love playing with my sister's easy bake oven. I love to cook. So much for gender stereotypes. Anyway, glad the 60s are gone. When people talk about the good old days, side note, why do old people talk about the good old days? Is it because they were good? Hell no. The good old days were horrible by today's standards. There was more violence. There was more poverty. There was more racism. There was more sexism. There was more, you name it, all the bad things, there were lots more of it. So why do old people talk about the good old days? Because they were friggin' 20 back then, and they were in great shape. And they felt good every day. So they remember how they felt back in the good old days. And they felt quite good compared to the way they feel now. So it was good for them. It wasn't necessarily good for everybody else. So anyway, that's Mike's lecture about the good old days. Let's see. In the 90s, they were rebranded Creepy Crawl. I remember those too. I remember Creepy Crawlies. And then you ran out of easy bake ingredients, and it became useless, and you can't find them at Walmart. Exactly. Yeah. Well, Andrew, obviously we could get political and talk about how it was good for very few select groups of people, and it was certainly better for some than for others. But if you look globally, different groups were on top, but the pile was still pretty crappy. People didn't live as long. People weren't educated as well. People, it's just, the world is better. When people stand there and talk about how terrible the world is today, there's no scientific data to back that up. If you look at anything you can measure, like poverty or education levels or life expectancy, anything like that, it all goes up with time, not down. So yeah, the good old days were pretty friggin' terrible. More terrible for some than for others, but pretty friggin' terrible. Okay, what does that have to do with computer science? I don't know. Let's see. So we talked about brightness. Okay, now how are we gonna begin to tie this to what we're doing in this class? Well, we're going to build models, lighting models, because we want our graphics to look more realistic. In the current assignment that you're working on right now, you just say, oh, one side of the pyramid is green, and one side is red, and one side is yellow. And you can paint it that way, but it looks very cartoonish. Or like toy blocks, right? It doesn't look It doesn't look illuminated. It doesn't look like a real object sitting in the real world. And that's what we want to do. We want to more closely simulate how light interacts with an object. And so we're going to, in reality, there tend to be light that comes from a particular source, from a particular direction. So think about the sun. If in the morning the rays are coming at an angle, at noon the rays are coming straight down from overhead. Towards evening they're coming in at an angle again. So light sources, point light sources, like the sun is essentially a point. It's so far away, it's kind of a point. Those can come at a particular angle. There are also diffuse light sources like your overhead fluorescent lights, where light is emitted from a surface. Now, there is no such thing in the real world as a point light source because a point is a mathematical concept. But you get the idea. If it's tiny, like the little LED on the back of your camera or back of your phone, we can call that a point light source because for all intents and purposes, it's a point. You could model it as a point, right? Whereas diffuse light sources, it's coming from a screen like your TV set or your monitor or our fluorescent light bulb. Okay, that's important because we'll get back to that later. So what about the perception of color? Why did I ask Jerry Berg what color was? And he tried to give more of a scientific answer, which saddened me. I wanted him to give more of an artist's interpretation. Because here's a statement that I'm sure he would disagree with. There is, or maybe he wouldn't if he sat down and he thought about it. There is no unique, unambiguous, real-world phenomenon that corresponds to what we humans call color. There is no unique, okay, in other words, a single thing, unambiguous, which means that you know it's this particular thing and not this other particular thing. There's no unique, unambiguous, real-world phenomenon, something in the world, something real, something that actually exists, a process or a characteristic. There's no unique, unambiguous, real-world phenomenon that corresponds to what we humans call color. Color is a characteristic of the human visual perception. That's what it is. Now, you should be going, what, wait, huh? Things like that. Because, haven't I been saying things like, well, green light is light with a wavelength of 550 nanometers, and red light is light, at 650 nanometers. So didn't I just tell you that, sure, light is something that's unique and unambiguous? It's a friggin' wavelength of electromagnetic energy. No, I didn't actually say that. I was very careful to say what I actually wrote here, which is that humans have attached names to many wavelengths of light. Humans have attached names to many wavelengths of light, such as red for a wavelength at 650, or green for a wavelength near 550, or yellow for a wavelength near 580. That is not the same thing as saying the colored yellow is defined as EM radiation at a wavelength of 580 nanometers. Those are different things. So what point am I trying to make? It sounds like I'm splitting hairs here. What am I actually trying to say? Well, I'm trying to make a very, very important point. And the point is that color exists in your head. Really. Yellow is in your head. Green is in your head. Blue is in your head. They're concepts that we humans have. But you might think, well, but okay, Mike, but but when I think red, you know, I'm really thinking, 650 nanometers of light. That's what I'm thinking. That's not really what you're thinking. Okay. We need to talk a little bit about human biology. And I already alluded to this. How do humans detect color? Well, we detect color because we have 3 types of color receptor cells at the back of our eye in our retina. These are called cones. They're called cones because they look like little upside-down ice cream cones if you look at them under a microscope. That's why they're called cones, because they actually physically look like cones. Now, sometimes you will hear someone say, and you'll hear me say it a little later on, oh, the red cones, the green cones, the blue cones. We really shouldn't call them that, because that brings to mind the idea that if you look under a microscope at a, quote, green cone, you'll see a little cone-shaped cell that's green. Green cones are not green. Green cones detect greenish light. Red cones are not red. They detect light that tends towards red. So the scientists that write about the biology of cones don't call them red, green, and blue cones, because that's misleading. They call them S cones, M cones, and L cones, because they're using that to describe the wavelengths that those cones are most sensitive. So S cones are most sensitive to short wavelengths of light, and L cones are more sensitive to longer wavelengths of light. And the M cones are the cones that are sensitive to light that's at a middle wavelength between the short cones and the long cones, between the S's and the L's. So you basically have 3 color receptors. Again, they're often called red, green, and blue receptors, but really it makes more sense to call them L for red, because the red wavelengths are longer wavelengths, M, which are the green cones, and S, which is the blue cones, because they're shorter. And here is the sensitivity of the cones. You might say, wait a second, didn't you give me something like this, Mike, that had 2 little thingies on it earlier, and now there are 3 little thingies? Well, this little thingy dealt with if you merge the sensitivity of your cones and your rods together and just pour in a fixed wattage of EM energy and vary that EM energy across flat, what you will see is a response curve here. So this is essentially 1 unit. You think of it as 1 watt. It's 1 unit of EM energy that varies. If you've got 1 unit of EM energy that's way down here, you're not going to see anything. But now if it's blue, well, if it's near night, if it's just your rods that are running, you'll get, what, about 80% input signal from that cell. If you're talking about daylight conditions, you're not getting very much at all, all right? If you are in the middle of the day and you've got greenish yellow light, right, it's peaking. Your overall input from your visual system is peaking. And then as that light, 1 watt of it, gets more towards red, your sensitivity falls way off. So that was like the combined sensitivity of your rods and your cones together under different lighting conditions, more intense light like daylight and dimmer light like towards evening and night. This is breaking that out and showing you the sensitivity of your S cones, your M cones, and your L cones. So your red cone is most sensitive to light. That's here, we call it red because we use it to distinguish red, but it's actually peaks in the around yellow, believe it or not. The M cones, we call them the green cones, and it peaks around green. We call this the blue cone, the S cone, and it's actually peaking a little before you get to what we would probably call blue. Anyway, again, every you know, different sources will draw these slightly different, the colors underneath here. But again, the short cones are the blue cones. They are most sensitive to shorter light. The M cones are the green cones. They're most sensitive to light somewhere in the middle of the spectrum that we can see. And the L cones are called the red cones. They're most sensitive to light that's shifted towards the right side. And you might see, surprisingly, these aren't equally spaced out. And in fact, the shapes of these things aren't even the same, right? It evolved. What can I say, right? And this is for humans. I need to specify this is for humans. Different animals have different sensitivities. As we'll see in a minute, color to a bird would be very different than color to a person. Okay. So, how do you see color? Well, you have these three detectors. That's all you have is these three detectors. You don't have some kind of input sensor that somehow registers uniquely, oh, I am being exposed to the wavelength 580 nanometers. You don't got that, okay? That's not built in your biology. If I expose you to green light, let's say not light at 550 nanometers, your body, your eyeball will detect that because your M cones and your L cones will be jiggling away, going, oh, I'm getting excited. I don't know why, but I'm getting excited. And your S cone will go, oh, I'm not feeling anything. I'm off, essentially, right? And so green is your M and your L cones are going, oh, I'm excited. And blue is going, I don't feel anything. That is how your body detects green. How does your body detect red? Your body detects red because your L cone is going, I'm real excited, and your green cone is going, I feel a little tingle down here, right? And your blue cone is going, wake me up when it's over, right? That is red. You know, the L is going crazy. The green is maybe jiggling a little, and the blue is off. That is red. What is blue? In blue, the short's going, oh, I'm so excited. And your M and your L are going, maybe I feel a tingle. Maybe. That's color. Those are the inputs. And when I say that's color, I'm saying that's all that the real world can do to stimulate our biology. Those are the only sensors that we got, okay? So from those sensors, your brain is just interpreting those signals, and we interpret that through color. So color doesn't really exist as a unique, unambiguous thing in the real world. You might say, well, Mike, okay, look, I get this jiggling, if you want to call it that, these intensity feelings along these, the response, use a little more science word, and okay, your brain is taking these things. But still, Mike, yellow is still friggin' yellow. And I go, not really. Okay. What do you mean, Mike? Why is it that Mike O'Neill says that color is not a unique, unambiguous characteristic of the real world? For two very important reasons. Humans can see colors such as yellow when their corresponding wavelengths aren't actually present. You can see yellow when it's not there, okay? And humans can see colors that don't correspond to any particular wavelength. So if you want to say, oh, color is just a wavelength of light, how do you explain that we can see colors that for which there is no wavelength of light. What do you say here? Let's take yellow. Let's take yellow light. Yellow light, we've said, is light at 580 nanometers we call yellow light. Okay, so how do we see yellow light? Well, like I said, you're going to detect 580 nanometers because your M cones are disco dancing, and so are your L cones. They're both getting huge responses here. That's how you see yellow. That's how you see 580 nanometers. But I can make you see yellow in two different ways. I can shine 580 nanometer light into your eye, and these cones will do their jiggling, and you'll say, I see yellow. Or I can send light in at this frequency, and I can send light in at this frequency, and if I adjust the intensities of those lights properly, your M cones and your L cones will jiggle in exactly the same way as if I had shined light at 580 nanometers in your eye, and you will see yellow, even though light at 580 nanometers isn't there. You see yellow. You get exactly the same sensation as if I had shined light at 580 nanometers in your eye, but I'm not doing that. I'm shining some light at a lower wavelength and some light at a higher wavelength, and I'm setting them at just the right intensity so that these two sensors get tripped at exactly the same levels that they would have been tripped at 580 nanometers. You're seeing yellow, and yellow isn't there. So if yellow was a real thing, right, I said that, okay, yellow, there is no unique, unambiguous. So when you see yellow, are you seeing 580 nanometer light, or are you seeing two different frequencies of light that just happen to be triggering your system to see yellow? That's not unique or unambiguous. Second thing, you might say, okay, well, that's making me think that things are interesting here, Mike. But it gets even weirder. You can see colors that don't exist. Well, obviously they exist. You see it in your head. You can see colors that do not correspond to a wavelength of light. So you cannot say that color is a particular wavelength of light because there's some colors that don't correspond to any particular wavelength of light. What do you mean, Mike? Well, you can see magenta. What is magenta? Well, magenta was a character in in the Rocky Horror Picture Show, but magenta is also a color, right, that is a bluish red color. Now, there can be no bluish red color, no wavelength for that, because blue is short wavelengths and red is long wavelengths, so they're on the opposite ends of the spectrum. But if I shine blue light into your eye and I shine red light into your eye, you see a color called magenta. When this guy's jiggling and this guy is jiggling and M is not really jiggling so much, you see that as magenta. But magenta is not a color that's in the rainbow. There is no wavelength of light for magenta. Magenta is just, I'm getting blue and I'm getting red at the same time, and your brain interprets that as a single color. Okay. So, that is why I say that light is not a, that color is not a unique, unambiguous thing in the real world. What does this have to do with computing? Well, it allows us to build color display devices. You're colorblind except for three sensors: the short, the medium, and the long wavelength sensors. So for humans, if I build a display where every point, every pixel can generate a wavelength that can stimulate your S sensor, your M sensor, and your L sensor, then I can build a display that'll generate any color that you can see, including magenta, which is a color that doesn't exist in the rainbow. So the reason why we have RGB displays is because you have 3 cones in your eyes, one that is sensitive to red, one that's sensitive to green, and one that's sensitive to blue. That's why we have RGB displays. And how do they work? Well, generally, we have usually pixels. Color systems are defined as 256 levels of red, 256 levels of green, and 256 levels of blue. Why 256? Because 2 hex digits, right, can hold that, right, 8 bits. That's why it's called 8-bit color, or 24-bit color if you do all 3 of them, right? And so usually you can represent a color as 6 hexadecimal digits. So red is FF0000. The first 2 are for red, the second 2 are for green, and the last 2 are for blue. So this is basically saying red is set to maximum, green and blue are off. Pure green is red is set off, green is set to maximum, blue is set off. Blue is 0000FF, etc. What about something like yellow? Well, yellow would be your red and your green set and your blue off. Okay. What about levels of gray? Levels of gray are where all of the colors are set at the same level. What about white? Well, white is FF, everything going at full bore. What about black? Well, you can't actually generate black color, but if you turn the pixel off and the pixels around it are bright white, the absence of that bright white, you'll see that as black. And that's one of the things is how do you make the blackest the blacks? That's a selling point in some displays. Anyway, I wanted to finish this up, but I think what I'll do here is I do want to say I need about 10 more minutes to finish up color, so we'll finish up color next time. If there's any questions, I'll be happy to take them. Otherwise, since I see we're already 2 minutes over time, I'm going to go ahead and end the class. We'll pick it up here on Wednesday. Have a great day, guys. Bye-bye.